6 Easy Pieces. Essentials of Physics Explained by Its Most Brilliant Teacher, by Richard P. Feynman. Introduction. If, in some great cataclysm, all of scientific knowledge were to be destroyed, and only one sentence could be passed on to the next generation of creatures, what statement would contain the most information in the fewest words? Think about that for a moment. One sentence to rebuild everything we know about the world. The man who asked this question was a physicist named Richard P. Feynman, and he had an answer. He believed the sentence would be this: all things are made of atoms? Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one simple idea, he said, lies an enormous amount of information about the world, if only a little imagination and thinking are applied. Welcome to the world of Richard Feynman. He wasn't just a Nobel Prize-winning physicist, one of the sharpest minds of the 20th century. He was something more, something rarer. He was a master teacher, perhaps the greatest of his era. He had this incredible, almost magical ability to take the most complex, most profound ideas about our universe and make them feel simple, intuitive, and deeply beautiful. In the early 1960s, Feynman took on the challenge of teaching introductory physics to freshmen and sophomores at Caltech. These lectures became legendary. They were less like lectures and more like performances, filled with wit, energy, and a contagious sense of wonder. The books that came from those talks, the Feynman Lectures on Physics, have inspired students and thinkers around the globe for decades. The book we're exploring today, 6 Easy Pieces, is a special collection. It contains the 6 most accessible chapters from those legendary lectures, chosen specifically for those of us who aren't physics majors. These chapters are Feynman's invitation to the rest of the world, a chance to see the universe through his eyes, without the need for complex mathematics. So, what is the promise of our journey today? It's not just to learn a few facts about physics. It is to catch a glimpse of the fundamental rules of the game of life. We're going to explore the simple principles that govern everything from the ripple in a pond to the light from a distant star. By the end of our time together, you will see the world around you not as a collection of separate, confusing things, but as a single, magnificent, interconnected story. And you will understand why Richard Feynman wasn't just a brilliant teacher. He was a guide to the poetry of reality. Book summary. Let's begin where Feynman himself began, with that one crucial sentence: everything is made of atoms. This might sound obvious to us now, but truly grasping its meaning is the key to unlocking almost everything else. Imagine a single drop of water. To our eyes, it's smooth, continuous, a single entity. But if we could magnify it 1 billion times, what we'd see is a chaotic, teeming dance. We would see countless tiny particles, the water molecules, each one a little group of atoms, 2 hydrogen atoms bonded to 1 oxygen atom. These molecules are never still. They are in a state of perpetual motion, jiggling, bouncing, and turning. This constant, random motion is what we call heat. When you heat water, you are simply making the molecules jiggle faster and more violently. They are all stuck together by a subtle attraction, which is why the water drop holds its shape. But if you add enough heat, the jiggling becomes so intense that the molecules break free from each other entirely. They fly apart, separating into a gas. That's what steam is. The same water molecules, just with more energy and more freedom. Now, imagine these steam molecules trapped in a container with a piston, like a cylinder in an engine. These tiny particles, each one impossibly small, are flying around and constantly bombarding the walls of the container. That collective, jittery force from trillions upon trillions of collisions is what we feel as pressure. If you squeeze the piston and compress the gas into a smaller space, the atoms hit the walls more often, and they also pick up speed from the moving piston. The gas gets hotter. This isn't some abstract rule. It's the direct result of the frantic dance of atoms. What if we go the other way? If we cool the water down, the jiggling slows. The molecules move less and less, and the attraction between them starts to take over. Eventually, they lock into a fixed, beautiful, crystalline pattern. We call it ice. In this state, each atom has a specific place, creating a rigid structure. Even then, they are not perfectly still. They are just vibrating in their fixed positions. As you cool them further, the vibration lessens, but it never stops completely, not even at absolute zero. There is a minimum amount of motion that atoms must always have. This one idea, The atomic hypothesis explains the states of matter, but it does so much more. It explains evaporation. From time to time, a molecule on the surface of water gets hit a little harder than its neighbors and gets knocked away into the air. That's evaporation, molecule by molecule. Since the molecules that leave are the ones with extra energy, the ones left behind have less average energy, which is why evaporation cools the liquid. It's why you blow on your soup to cool it down. You're simply clearing away the vapor, encouraging more high-energy molecules to escape and take their heat with them. So, if everything is made of these jiggling atoms, what holds them together and pushes them apart? What are the rules of this cosmic game? Feynman explains that science is like watching a grand chess game played by the gods. We can't ask the players what the rules are. All we can do is watch. If we watch long enough, we start to notice patterns. A bishop always stays on the same color. A pawn moves forward, but captures diagonally. These are the rules, what we call the fundamental laws of physics. For centuries, we thought the rules were incredibly complicated. We saw heat, electricity, magnetism, and motion as completely separate things. But the goal of physics, Feynman says, is to see the complete picture, to realize that these are all just different aspects of the same underlying phenomena. The first great unification of these rules came from understanding the forces between atoms. Gravity, the force that holds the planets in orbit, is far too weak to explain how atoms stick together. The real force at play is electricity. Imagine, Feynman says, that instead of everything attracting everything else, like gravity, there are two kinds of stuff, positive and negative charges. And the rule is simple. Likes repel, and unlikes attract. This force is tremendously powerful, millions of times stronger than gravity. So why don't we feel it all the time? Because most objects, including our own bodies, are made of a near-perfect balance of positive charges in the nucleus of atoms and negative charges, the electrons surrounding them. The attractions and repulsions cancel each other out on a large scale. But when atoms get very close to each other, they can see inside and rearrange their charges, leading to the strong interactions that we call chemical bonds. Every chemical reaction, from the burning of wood to the complex processes in our cells, is governed by this dance of electrical attraction and repulsion. The story of discovering these rules is a grand adventure. It began with the ancients watching the planets wander across the night sky. For centuries, we argued about how they moved. Then came the astronomer Tycho Brahe, who had a revolutionary idea. Instead of arguing, let's measure. He spent years meticulously recording the positions of the planets. After his death, his assistant, Johannes Kepler, used that mountain of data to discover three simple, beautiful laws. First, the planets don't move in perfect circles, but in ellipses, with the sun at one focus. Second, they move faster when they are closer to the sun and slower when they are farther away, in such a way that they sweep out equal areas in equal times. And third, there is a precise mathematical relationship between how long a planet takes to go around the sun and its distance from it. Kepler knew how the planets moved, but not why. That question was left to Isaac Newton. Newton, armed with Galileo's idea of inertia, the principle that an object in motion stays in motion unless a force acts on it, had a brilliant insight. To keep a planet in orbit, you don't need to push it forward. The angels don't have to fly behind it. You only need to pull it inward, toward the sun. By analyzing Kepler's laws, Newton deduced the nature of this force. It had to be a pull that got weaker with distance, in proportion to the inverse square of the distance. And it had to be universal. Every object in the universe attracts every other object. He tested this idea by calculating the force needed to hold the moon in its orbit around the Earth. He compared it to the force that makes an apple fall from a tree. After accounting for the vast distance to the moon, he found that the force was exactly the same. It was a perfect match. This law of universal gravitation explained so much. It explained the tides, the shape of the Earth, a slightly flattened sphere due to its rotation, and the wobbles in the orbits of planets caused by the pull of their neighbors. In fact, when the planet Uranus was found to be deviating from its predicted path, astronomers used Newton's law to calculate the position of an unknown planet that must be pulling on it. They pointed their telescopes to that spot, and there it was, the planet we now call Neptune. But even with this understanding of atoms and forces, there's another piece of the puzzle, another fundamental rule of the game. It's a strange, abstract law that governs all of nature without exception. It is the law of conservation of energy. Feynman explains this law with a wonderful analogy. Imagine a child, Dennis the Menace, who has 28 indestructible blocks. His mother leaves him to play in a room. At the end of the day, she counts the blocks and finds there are always 28. One day, she counts only 27. After a search, she finds one under the rug. The law is safe. Another day, there are only 26. She looks out the open window and finds the other two outside. To check the law, she must make sure none have been added or taken away. Then, one day, she counts and finds only 25. She sees a toy box, but Dennis won't let her open it. Being a clever mother, she devises a scheme. She knows each block weighs 3 ounces. So she weighs the box when all 28 blocks are visible and finds it weighs 16 ounces. From then on, she can calculate the number of hidden blocks by weighing the box, subtracting 16 ounces, and dividing by 3. She discovers a new formula. The number of blocks she can see, plus the weight of the box minus 16, divided by 3, always equals 28. As the child's world gets more complex, she has to add more terms to her formula, one for the level of the dirty water in the bathtub where he might be hiding blocks, and so on. She ends up with a complex calculation that always gives her the same number, 28. The most remarkable part of the analogy, Feynman says, is this. In the real world, there are no blocks. Energy comes in many different forms: gravitational energy, kinetic energy, the energy of motion, heat energy, chemical energy, electrical energy, and more. For each form, we have a formula, a way of calculating a number, just like the mother weighing the toy box. And the law of conservation of energy states that if you add up all these different numbers, the total sum never, ever changes. Energy can transform from one form to another, but the total amount always remains constant. When you lift a weight, you give it gravitational potential energy. If you let it fall, that potential energy is converted into kinetic energy. When it hits the ground, that kinetic energy is converted into heat energy, jiggling the atoms in the ground and the weight. The number, the total energy, stays the same. This principle is incredibly powerful. It allows us to understand how machines work, how chemical reactions produce heat, and even how stars shine. The sun's energy comes from nuclear reactions in its core, where the mass of hydrogen atoms is converted into helium and a tremendous amount of energy, according to Einstein's famous formula, $E equals mc². We now have a picture of a world made of atoms, governed by forces, and ruled by the conservation of energy. It seems clean, logical, and predictable. But this classical view of the world, as beautiful as it is, breaks down when we look at things on the smallest possible scale. This brings us to the final, and most mysterious, piece of the puzzle: the world of quantum mechanics. Feynman tells us that things on a very small scale behave like nothing we have any direct experience with. They are not like waves, not like particles, not like anything we've ever seen. To illustrate this, he asks us to imagine another experiment, the most important thought experiment in modern physics. Imagine we have a gun that shoots tiny bullets at a wall with 2 small slits in it. Behind the wall is a backstop that detects where each bullet lands. If we close one slit, say slit 2, and fire the gun, we get a simple pattern of hits behind slit 1. If we close slit 1 and open slit 2, we get a similar pattern behind slit 2. Now, what happens if we open both slits? The answer is obvious. The total pattern will just be the sum of the 2 individual patterns. The bullets go through one slit or the other, and the probabilities simply add up. There is no interference. Next, let's do the same experiment with waves, like water waves in a shallow tank. A source creates waves that travel towards the wall with 2 slits. When the waves pass through the slits, they spread out and interfere with each other. In some places, the crests of the waves from both slits arrive at the same time, adding up to create a bigger wave. This is constructive interference. In other places, a crest from one wave arrives with a trough from the other, and they cancel each other out. This is destructive interference. The result is a beautiful pattern of highs and lows on the detector, an interference pattern. The intensity when both slits are open is not the sum of the intensities of the individual slits. Now for the final, crucial experiment. We replace the gun with a source that fires electrons, the tiny particles that make up atoms. What pattern do we expect? Electrons are particles, like tiny bullets, so they should behave like bullets, right? They should go through one slit or the other, and the pattern should be the simple sum of the two. But that is not what happens. When we fire the electrons, they arrive at the backstop one at a time, in distinct lumps, just like particles. We hear individual clicks from our detector. But when we plot the probability of where they land, the pattern that emerges is the wavy, striped pattern of interference. It's the wave pattern. How can this be? The electrons are arriving as particles, yet they are distributed as if they were waves. It seems as though each individual electron, traveling by itself, is somehow interfering with itself. This result is the central mystery of quantum mechanics. It defies all common sense. We might argue, well, obviously each electron must go through either slit 1 or slit 2. This seems like a reasonable statement, what Feynman calls proposition A, but if it were true, the probabilities would have to add up, and they don't. The interference pattern proves that proposition A must be false. But wait, what if we try to watch? What if we put a bright light source right behind the slits, so we can see a flash of light whenever an electron passes through one of the slits? Now we can check. We run the experiment again, and here is what we find. Every time a click is heard at the detector, we see a flash of light near either slit 1 or slit 2. But never both at once. When we watch, the electrons do go through one slit or the other. Proposition A is true after all. But now a new mystery emerges. When we look at the pattern the electrons make on the backstop while we are watching them, the interference pattern is gone. It has been replaced by the simple, non-interfering pattern of the bullets. The very act of observing which path the electron takes destroys the interference. It's as if the electron knows it's being watched. The light we use to see the electron, even a single photon of light, gives it a little jolt that disturbs its motion just enough to wash out the delicate interference effect. This leads to the famous Heisenberg uncertainty principle. It's impossible, Feynman explains, to design an experiment that can determine which hole the electron goes through without, at the same time, disturbing the electron enough to destroy the interference pattern. There is a fundamental limit to what we can know about the world at this scale. We cannot know both where an electron is and where it is going with perfect accuracy. So, does an electron go through one slit or the other? The only answer quantum mechanics gives us is this. If you set up an experiment to check, the answer is yes. If you don't, the answer is no. You cannot say it goes through one or the other when you are not looking. This is the strange, beautiful, and deeply counterintuitive reality of our universe. Everything, electrons, protons, even photons of light, behaves in this dual way. They are all particle waves. The laws that govern them are not laws of certainty, but laws of probability. Physics has had to give up on the dream of predicting exactly what will happen. It can only predict the odds. And so, from the simple, tangible dance of atoms in a drop of water, we arrive at the ghostly, probabilistic world of quantum mechanics. This is the grand picture that Feynman paints for us. It's a world built from simple rules, but those rules lead to a reality more complex, more mysterious, and more wonderful than we could have ever imagined. Physics, in this view, is not just a subject in a textbook. It is the quest to understand the deepest workings of nature, a quest that reveals the profound and beautiful connections between all things. Commentary. As we step back from the details of Feynman's 6 easy pieces, what is the feeling we are left with? It's not just an appreciation for physics, but a profound sense of awe for the universe itself, and for the human mind's capacity to comprehend it. The most powerful lesson in this book isn't about atoms or energy or quantum waves. It's about a way of thinking. Feynman shows us that science is not a collection of boring, memorized facts. It is a living, breathing process of discovery, driven by a relentless curiosity and a deep humility. The first step to understanding, he teaches us, is to admit that we don't know. He had a healthy disrespect for received wisdom and stuffy formalism, preferring instead to approach every problem with a fresh, intuitive eye. He reminds us that the universe is not obligated to make sense to us. Things on a small scale don't act like things on a large scale, and that's not a problem to be solved. It's a reality to be accepted and explored. This is a deeply humbling idea. It asks us to let go of our comfortable, common-sense view of the world and embrace a reality that is fundamentally strange and mysterious. But it is also incredibly empowering. Feynman shows us that with just a few simple, elegant laws, like the atomic hypothesis and the law of gravitation, we can explain a staggering variety of phenomena, from the color of the sky to the life cycle of a star. He shows us that the same rules apply everywhere. The atoms that make up the distant stars are the same atoms that make up you and me. As he once beautifully put it, I too can see the stars on a desert night, and feel them. But do I see less or more? The vastness of the heavens stretches my imagination. Stuck on this carousel, my little eye can catch 1 million-year-old light. What is the pattern, or the meaning, or the why? It does not do harm to the mystery to know a little about it. So, how can we carry the spirit of Feynman into our own lives? Here are a couple of simple ideas. First, practice seeing the unseen. The next time you see something simple, like ice melting in a glass or a ball rolling to a stop, take a moment. Try to visualize the frantic dance of the atoms beneath the surface. Picture the potential energy converting to kinetic energy, and then to the random jiggling of heat. By doing this, you're not just observing the world, you are connecting with its fundamental reality. You are seeing more. Second, embrace the mystery. We live in a world that demands answers, certainty, and quick solutions. But Feynman teaches us that the greatest engine of discovery is the willingness to say, I don't know. When you encounter something that confuses you, don't see it as a failure of your understanding. See it as an invitation. The most interesting phenomena, he said, are in the places where the rules don't seem to work. That is where the next discovery lies. Cultivating that sense of wonder and comfort with uncertainty is the true heart of the scientific spirit. That was a summary of 6 easy pieces by Richard P. Feynman. We've touched upon the core ideas today, but I have to be honest with you. A summary is like looking at a photograph of a breathtaking landscape. You can see the shape of the mountains and the color of the sky, but you can't feel the warmth of the sun or the gentle breeze on your skin. The real magic of this book is in Feynman's voice, in the joyful, irreverent, and brilliant way he guides you through these ideas. This summary is here to help you decide if this journey is one you want to take. If anything we've talked about today has sparked your curiosity or made you look at the world a little differently, then I encourage you to pick up a copy. Reading it isn't just about learning. It's an experience that can genuinely change the way you see the universe and your place within it. The link to the book is in the description below. Also, if you found this summary valuable, please take a moment to hit that like button and subscribe to Billionaire's Bookshelf. Your support helps us continue to explore these incredible books together, and it ensures you won't miss our next deep dive. Let's keep learning and growing, one book at a time.